Hello, so in this video we're going to talk about a slightly different technique of how we can solve first order differential equation. It's perhaps looking at a differential equation from a different point of view. So kind of up until now we've been given, say like a differential equation, dy by dx equals some function involving the variables x and the function y. Okay, so y is dependent on x as well. But basically, we get given this differential equation and we get asked to find the solution from this. So in other words, we get asked to find what that function y is that satisfies this equation. Okay. Well, now what we're going to do is we're going to do it from the other point of view. So in other words, we get given the solution, okay, and we get asked to find an ODE which satisfies that solution. All right. And the process is really quite straightforward and really quite simple. So the idea is obviously we get given a solution y. So obviously, in order to get what the differential equation is, we're going to have to differentiate it because it involves a derivative. So therefore, in order to have a derivative in the equation, we're going to have to differentiate it. So we know that one of the steps is going to be differentiate. Okay, we know that one of the steps is going to have to be differentiate in order to get, a derivative involved. Okay, but also, we get given what's known as a family. We call it a family of curves. And the reason why we call it a family is because we normally get given a solution involving constants. We say like C1, C2, etc. Excuse me. So we get given the constants. And that's why it's called a family, because, if you like, the constants basically mean if we have something like y equals, I don't know, y equals cx squared, or x squared plus c, should we say? X squared plus c, should we say? So this would be known as a family because this constant could literally be anything. So when we draw it, we effectively get some curves that all follow the same shape, but they fall in slightly different places on the plane, okay? They're all the same shape, but they fall in slightly different places on the plane, and that's because of this constant on the end. So that's why it's called a family. It's a family, if you think about it, in a family, all the people are related to each other, so they can all kind of share, they all share the same DNA, if you like, but they're all sort of slightly different, okay? And in order to determine which member of that family we want to deal with, we have to know the constants effectively. We have to know some data about it. Okay, so this is kind of why it's called a family of curves. And so effectively, all we're just doing is we're going to find out what this differential equation is. Okay, and the idea is that basically we need to also eliminate constants. Okay, because we can't have a differential equation involving constants. If we have a differential equation involving constants, then we potentially open ourselves up to have more solutions than just the solutions that we're given. So in other words, when we go back the other way, we find when we have the differential equation, we want to then find the solution from that. We go back the familiar way that we're used to. If we've got constants involved in this one, effectively we can have more solutions. We can have kind of like extra solutions, if you like, because we've got constant in here. So kind of we're going to have to, along some point, we're going to have to eliminate the constants to get a differential equation not involving constants effectively, so then we don't have too many solutions. All right, so that's kind of the main two, those are the main two processes. Okay, and eventually what we want to end up with is we want to end up with a differential equation that involves derivatives. So we want to end up with an equation that just involves the derivatives based on our solution. Okay, the solution is derivatives. So the best way of seeing it is through an example. So I want to give you an example. We get given, I'm going to call it example, or no, this is the example. So cy minus sine of that same constant times x. Same constant c times x. Okay, and that equals 0. So we want to now find a differential equation that defines this family of curves. Right. So the first thing that we're going to do, just for kind of notation's sake, we're actually going to let f equal this. Okay, we're going to say, well, this is a sum function, and we're going to call that function f. And what is dependent variables? You don't have to write the dependency, but it's always, in case you're interested in. Okay, we've got y, okay, and y is going to be dependent on variable x as well. So we've got a function which involves x and y is dependent on x as well. Okay, so this is what we've got. Okay, so the first step is we need to differentiate it, because obviously we need the derivatives involved. At the moment, this hasn't got any derivatives in, so it's not a differential equation. But if we want to turn it into a differential equation, we're going to have to include the derivative. So first things first, let's differentiate this function with respect to x. Let's just differentiate it. Remember that y is a function of x. I always, when I'm dealing with these kind of questions, I always write y is dependent on x, just to remind me that y is a function dependent on x. So when I'm differentiating with respect to x, I don't just treat y as a constant. Yeah, it is actually a function. So what do we end up with? Well, c is a constant, and it's going to be multiplied by my derivative of y. Yeah, so y of x, right? Minus, because I've differentiated this term, okay? Minus, well, this term differentiated, it's just a chain rule, the Altini rule. So I differentiate the sign first to go to cos, leave the inside alone, okay? Then I multiply that by the derivative of the inside. By the derivative of the inside, well, what's the derivative of the inside? Well, the derivative of cx is going to be just c, and we're going to multiply that by the cos x. Okay, so that is the derivative. Okay, and of course the derivative of 0 with respect to x is of course 0. So this is all equal to 0. Okay, so this is now in the form of an ODE. Okay, this is actually an ODE, except for the fact that I've got constants, and these constants are kind of really annoy me because I'm going to end up with more than I need. So basically, now what I need to do is try and get rid of my constants. Well, in order to do that, you know, sometimes there's different ways of doing it. Sometimes you just have to follow your mathematical intuition and kind of, you know, wing it, basically. Kind of, yeah. So the first thing I'm going to do is I'm going to use this, and I'm going to use this, and I'm going to try and use these two equations now to try and eliminate the constants. I've got two equations. I've got this equation up here, and I've got this equation up here. And I'm going to try and eliminate the constants using those equations. So first of all, I'm going to use this equation up here, this cy. Okay, I'm going to drop the dependence on x now because I've got everything, you know, I don't need to worry about the dependence on x now. Minus c sine cx equals 0. First things first, I'm going to take this sine over to the other side to make it look like that. Okay, now I can say, well, okay, y is just going to be equal to, actually no, I'll just leave it like that. I'll just leave it like that, funny enough. Okay, now this, I'm going to do the same kind of thing. I'm going to have cy dash is going to be equal to, so cy dash minus c cos cx equals 0. Okay, I'm going to take the sign c cos x over to the other side, and I'm going to end up with this. So basically, I've just rearranged these two things to get this. Okay, to get this. Okay, well look, do you know, well look, I could just cancel off the c's here. Happy, I'll just cancel off the c's, just divide through by c. Well look, I've got a sine here, and I've got cos here. Now I know of an identity involving sines and coses, right? I know that sine squared plus cos squared, I've got the same angle in both, so I don't need to worry about the angle, the argument, okay? Sine squared plus cos squared equals 1, all right? So basically, the idea is that if I square these two things, okay, so this is, I'll just write the identity out again involving my angle, so this is sine squared of cx plus cos squared of my angle, cx, that's got to be equal to 1. Okay, so in other words, if I square these two things, I can make use of this identity. So if I square this thing, it's going to go to, well, if I write it out again, actually. So if I square this top thing, then it's going to end up with, well, the right-hand side is going to be sine squared cx, right, which is what I want in this. That's what I want in this. Then what's the left-hand side going to do? Well, it's going to be cy all squared, which of course I can write as c squared y squared. Excuse me. Okay, now let's try and do the bottom side, so the bottom one, so this one here. So I end up with, the right-hand side is going to be cos squared cx, which is good. That's exactly what I want down here. But what's the left-hand side going to be? But it's going to be y dash all squared. Okay, so now I can basically say that this plus this is going to be equal to 1. So in other words, sine squared plus cos squared is equal to 1. So just now using the left-hand side, so this is c squared y squared, okay, plus this one, plus y dash all squared. Okay, that's got to be equal to 1. So therefore I can say that now c squared, so c squared y squared. So remember, I want to find out what c squared is, right? And then I can just plug it back into a differential equation here. So c squared y squared is equal to minus y dash squared, okay, divide through by y squared over y squared. Sorry, this is 1 minus, isn't it? Oops. Let's rewrite that again. That's 1 minus y dash all squared. Okay, then divide through by y squared. I end up with that. So therefore C is just going to be equal to this. C is going to be equal to this. So therefore, using my differential equation, which was y dash equals cos cx, right, that was my differential equation that I found here, because I found an equation that links my derivatives, that had a derivative in. Okay, so y dash equals cos cx, then was c is what I've just found up here. So cos of, well, it's going to be x times square root of 1 minus y dash all squared over y squared. Okay, and there we go. So this is my differential equation. Nice and easy. So basically the idea is that you end up with a differential equation. You know, you basically want to end up with an equation that has derivatives in. Okay, that links derivatives and your functioning. And yeah, and then you don't want any constants in. So those are the two main ideas behind it. Let me do a slightly more demanding, slightly more difficult example. Here we are. So, oops, go away. Here we go. So we end up with x minus c1 all squared plus c squared. So yeah, that's c2. c2 y squared equals 1. All right. So again, the first things first, I want to note that this isn't just y. This is y of x all squared. Okay, so just so you don't get confused, don't treat y as a variable and just, you know, try and differentiate y with respect to x and get 0 or just a constant. Okay, you want to actually treat it as a function dependent on x. Okay. Excuse me. So again, first things first, I want to let all of this thing equal some function. The dependence is again going to be y on x and x. Okay, so that's my function. Again, first things first, I want to differentiate it. Now, how many times do I have to differentiate it? Well, a good tip is always look at the highest power associated with x. So here's my x in here, okay? And I want to look at the highest power which is associated with x, and in this case it's 2. So because it's squared, that tells me that my highest power is going to be differentiating twice. Okay, I'm going to have to differentiate twice. So let's differentiate once. So differentiate f once. Okay, what do I get? Well, I get the derivative of this thing. Well, I can just use a chain rule for that. Okay, I can differentiate the outside and leave the inside, which is the x minus c1 alone. So effectively, I'll just ignore, you know, I just treat this as treat this as kind of like one variable. So it's just 2, lots of the inside left alone, okay, to the power of 1. I'll just write that. Okay, multiplied by the derivative of the inside. What's the derivative of the inside with respect to x? This is a constant, okay, so therefore it's just going to be 1 anyway. So this is just the derivative of that first thing. Right, plus then the derivative of this thing. Well, it's going to be c2 is just a constant. Okay, what's the derivative of y squared with respect to x? Remember, y is a function. Okay, so remember that y is a function. So therefore, it's going to be 2. Again, just treat using the chain rule. Just treat it using the chain rule. Okay, so leave the inside alone because effectively this is a function inside. So just leave the inside alone. So bring down the 2. So it's 2, lots of the inside left alone, y of x, all to the power of 1. Okay, so we can just write that. Okay, times by the derivative of the inside. Well, the derivative of the inside is going to be y dash of x. Okay, the derivative of y with respect to x. I'm just going to tidy this up by writing 2c2 at the front. That looks neater. Okay, and equals the derivative of 1, which is going to be 0. Okay, so now I've got this written down. So hopefully you can see how I've got everything now. This is just the chain rule. Okay, it's just the chain rule. The same chain rule that we used here, actually. Okay, so what's now the second derivative? So I've got the first derivative. What's the second derivative? Okay, because again, I know that I'm going to have to differentiate twice by this power up here. So what's the second derivative? So again, it's just the derivative of this thing. All right, so again, chain rule. It's going to be 2. Is just my constant. Oh, it's not the chain rule, actually. It's just the derivative of this side. 2 is just my constant. So what's the derivative of the thing inside? It's going to be, well, it is a chain rule, actually. What's the derivative of the thing inside? It's just going to be 1. So it's going to be 2 here. All right? Plus 2. This is now the product rule. This is now the product rule because I've got the product of two functions. So it's going to be 2c2 times the first thing differentiated, which is y dash, times the second thing left alone, which is y dash of x. Okay? Plus, again, the same constants, plus the first thing left alone, which is y of x, times the derivative of the second thing, which is y double dash of x. Okay, and that's got to be equal to 0. All right. Now all I'm just going to do here is actually I can see a 2 here, 2 here, 2 here. So it's a 2 associated with every single term. So all I'm just going to do is just divide through by 2 to make things a lot easier. So end up with 1 here, again 1 here. So therefore 0 divided by 2 is still 0. Okay, so I just simplified that down a little bit more. Okay, and I'm going to call this one, actually I'm going to call this one equation 1. So my original equation is equation 1. My second equation is going to be equation 2. So my first derivative is going to be equation 2. And my second derivative is going to be equation 3. Okay. So now my aim is to try and eliminate the constants. Well, look, I've only got a C2 involved in this second derivative. So therefore, what I'm going to do is I'm going to try and find out what C2 is from the second derivative. So from 3, which is my second derivative, this thing here. Okay, I'm going to try and find out what C2 is. So I've got y plus C2. I'm going to drop the dependence on x just so you can see it a little bit better, hopefully. This is y dash times y dash. Well, I can write this as y dash all squared then, because it's y dash times y dash. Plus C2, y times y double dash equals 0. So again, I've just dropped the dependence on x, just to make things a lot easier. Okay, so first things first, I'm going to take this 1 over to the other side. So end up with minus 1 here. Okay, then I can just factor out C2. So factor out C2 out of this thing, end up with that. Okay, divide through by this thing, end up with C2 equals minus 1 over y dash all squared plus y times y double dash. Alright, okay, so that's what C2 is now. I've found out what C2 is. Okay, so now I can use C2 to find out what C1 is in 2, so by putting it back in 2, so using C2 in 2, okay, what was 2 again? It was 2 times x minus C1 plus 2 times C2. Well, I now won't know what 2C2 is. I know what C2 is. It's this thing here. So it's going to be minus 2 times C2, which was y dash squared plus y double dash. Yeah, it's just that thing there. So, and that's going to be multiplied by y times y dash. So y dash. Okay, so that's effectively what C. So now I can hopefully rearrange this, and that's all equal to 0. Now I can hopefully rearrange all this to find out what C1 is. So I end up with 2 again, 2 here, so I can cancel those off, divide through by 2. Okay, so end up with x minus C1 minus y dash over y dash squared plus y double dash equals 0. Well, I'm going to take this last term over to the other side. Okay, so I'm going to take this over to the other side. So I get that. Okay, so now what's C1 equal to? Well, C1, actually no, I'm going to leave that there. So that's equal to 0, and I'm just going to take C1 over to the other side. That makes more sense, isn't it? So in other words, C1 is equal to all of this thing. C1 is equal to all of this thing. Okay, so I've now found an expression for C1. Alright, so this is my expression for C1. Now what I want to do, so now I know what C1 and C2 is. Let me just write what C1 was. So C1 equals x minus y dash over y dash all squared plus y times y double dash. And C2 is minus 1 over y dash all squared plus y times y double dash. And this is my original function. So x minus C1 all squared plus C2 y squared equals 1. Okay, so now what I want to try and do, now notice that if I just substitute C1 and C2 in to this original equation, because my constants involve derivatives, okay, then that is enough to get a differential equation out. Remember, all a differential equation is just an equation that links derivatives and functions together. Okay, that just has functions and derivatives in, and derivatives of those functions in. Okay, so therefore, if I just substitute C1 and C2 back into my original equation, then I automatically get just a differential equation. Okay, I could equally put it back into, where are we? I could equally put C1 and C2 back into this first derivative, okay, and get kind of, exactly, pretty much the same, get another differential equation. And equally, I could put C2 back into this thing and again get another differential equation. Basically, because I'm just ending up with equations, it doesn't matter where I put my constants. So I'm going to put my constants, just for argument's sake, I'm just going to put it back into my first equation. Okay, I mean, you can try actually putting it back into the second equation and put it back into the third equation. So, in other words, the first derivative and the second derivative. And you just end up with a differential equation exactly. You just end up with a differential equation. It doesn't matter which one you put it into. As long as you end up with an equation that has derivatives in and functions in, then you've found the differential equation. Okay, so let's have a look at this. You may even find that there'll be cancellations and you get the same differential equation out. But let's have a look at this. So this is x minus c1. So x minus c1. So this is x minus c1, which was x minus y dash, y dash over y dash all squared plus y double dash. Okay, that's all squared. That's all squared in there. There we go. So that's that first bit dealt with in there. Okay, plus c2, which is minus 1 over y dash all squared plus y double dash, okay, times y squared. So I'm just going to write the y squared on the top then, is equal to 1. Okay, so that's fine. So now all I'm just going to do is I'm going to try and do a little bit of rearranging. So this is minus, if I just multiply this minus through. Well, these cancel out. This x and this minus x effectively just cancel out, right? So I end up with, what do I end up with? Y dash over y dash all squared plus y double dash, and that's all squared, okay, minus y squared over y dash all squared plus y double dash. Oops, let's fit a little bracket in there. There we go, and that's all got to be equal to 1. Well, first things first, I want to just deal with this square bracket here. So this squared means the top squared over the bottom squared. Okay, so I can just rewrite that as the top squared over the bottom squared. Okay, well, this bottom here is exactly the bottom of this fraction here is exactly the same as the bottom of this fraction here. It's just raised to a different power. So in other words, if I multiply this second fraction by this same denominator, so in other words, multiply this denominator by itself, I'll get the same denominator on both. So in other words, if I just write this squared times, just make room, y dash all squared plus y double dash, okay, and that's all going to be equal to 1, then I get the same denominator on both. So I've just multiplied top and bottom by y dash all squared plus y double dash, okay, and I end up with the same denominator on both. Well, now I can just multiply through by this denominator. I can just now multiply through by this denominator, because those two denominators will cancel. Then on the right, I'll just end up with y dash all squared plus y double dash, okay, and that's all squared. That's all squared. So in other words, if I just multiply through by that, I get rid of these fractions on the left-hand side. Okay, so what's going on here then? Well, this is y squared, y dash squared. Yeah, y dash squared. Okay, so that's that thing expanded. Minus, let's expand this bracket out. So it's minus y squared, y dash all squared. Careful of the minus, because it's minus y squared, y times y double dash. Well, this now becomes y squared times y, which is y cubed. Okay, and that's got to be equal to y dash all squared plus y double dash all squared. Okay, notice these two things are the same, so they can cancel out. So that minus that, so that cancels out. So therefore, that thing, if I take this y cubed y double dash over to the other side, I end up with y cubed y double dash plus y dash all squared plus y double dash all squared, and that's all going to be equal to 0. And therefore, I've found a differential equation that satisfies my original family of curves.